Alright guys, let's talk about an RC circuit. That is a circuit that has a resistor and a capacitor. And we're gonna assume that this circuit has been, that we have a battery that has been connected, the way you can see in the picture. That this connection has been there for a while. The switch has been closed for a certain amount of time. So we have charged the capacitor to a difference in potential equal to the voltage of the battery. So that's what the situation that we have. Then suddenly we're gonna open the switch at t equals 0. We're gonna open the switch so that, as you can see, the battery is now out of the picture, and we have a loop formed by the capacitor and the resistor. So only capacitor and resistor are playing a role in this circuit. That's what we call it an RC circuit. So at t equals 0, the switch is open, and there is a current that is going to start flowing out of the capacitor. The capacitor is going to discharge through the resistor. The direction of the current, you can see, is going to be counterclockwise. I'm assuming that the positive side of the capacitor is as indicated there. So Kirchhoff's loop law applied to this loop. If we start at point O and we move counterclockwise, we encounter an increase in potential going from the negative plate to the positive plate of the capacitor. That's a delta VC that is going to be positive. And then as we move through the resistor, we have a drop in potential of I times R. So these two differences in potential need to be equal to each other. Delta VC is going to be equal to IR, the current through the resistor times the resistor. And the difference in potential across a capacitor, we have studied before, that is equal to the charge in the capacitor divided by the capacitance. So we can write Q divided by C equals I times R. Now one more thing to do here to solve this equation and find out how the charge in the capacitor changes with time is to notice that since the capacitor is discharging, the current, as we indicated there, coming out of the positive plate of the capacitor, if we say that that current is positive, given the fact that the capacitor is discharging, dq dt is negative, the charge is going down, then the proper relationship between the current in the circuit and the charge of the capacitor should be I equals minus dq dt. Again, dq dt is negative, so with a negative in front becomes positive, so that we get a positive current, since we are calling the positive that is flowing, the current that flows in the counterclockwise direction, we're calling that positive. So using that, we can write the equation before as Q over C equals minus dq dt times R. Now this is a differential equation. We have the variable, the function Q of t, and its derivative related to each other through an equation. So that is a differential equation of the first order, and the way we deal with those equations in physics is that we separate the differential symbols that make up the derivative. So we write the equation, as you can see there, as minus dt over rc equals dq over q. So with this separation of variables, then we can proceed to integrate on left and the right side of the equal sign, and the integral has limits. For time, we're integrating from t equals 0 to some time, and at t equals 0 we're going to say that the charge in the capacitor was q naught, and that at t, some later time t, the charge is q of t. So these are our limits of integration. So the integral on the left hand side is minus t over rc. The integral on the right hand side is natural logarithm of q of t divided by q naught. And solving for q over q naught, exponentiating on both sides, we get e to the minus t over rc equals q over q naught. And our final expression for the charge in the capacitor is q naught, the initial charge in the capacitor, times a negative exponential function. So as we can imagine, the charge in the capacitor decreases, and it decreases, according to this equation, exponentially. So a graph of the charge in the capacitor as a function of time looks like that, and after an amount of time equal to R times C, the charge in the capacitor has dropped to 37% of its original value. That's because if you replace t equal rc, you get that the charge in the capacitor is q naught times e to the minus 1. E to the minus 1 is 0.37, so the value of rc gives us an idea of how quickly the capacitor discharges. This quantity RC is called the time constant. We use the letter tau equal RC to talk about the time constant of this RC circuit. The product of the resistance and the capacitance gives us an idea of how quickly the capacitor is going to discharge. If you do the math, you will notice that the charge in the capacitor drops to 5% of its original value after an amount of time equal to 3 times the time constant. After 3 times RC, we are down to 5% of the original charge. Now, what is the current? The charge goes down exponentially. What about the current that flows in the circuit? The current, as we said before, is going to be the negative of the derivative of the charge with respect to time. We have the equation for the charge, so we take the derivative of that exponential function. The argument of the exponential is minus t over rc, so the derivative of that gives us the minus 1 over rc term in front. The exponential remains, so we basically get that the current flowing in the circuit is going to be Q naught divided by rc times the exponential e to the minus t over rc. Now notice that the initial charge in the capacitor divided by the capacitance is the initial voltage of the capacitor. So that's the initial voltage that we have applied to that resistor. So the initial voltage divided by the resistance is the initial current flowing in the circuit. At t equals 0, that's the current that starts to flow in the circuit. And as the capacitor gets discharged, the current is going down exponentially, just like the charge in the capacitor. So that's our final result for the current as a function of time flowing in this RC circuit, starting with the capacitor charged. Now let's take a look at another kind of circuit, a circuit that uses a inductor connected to a resistor. But first, let's take a look at the inductor. What is an inductor? The inductor is characterized by a number called the self-inductance. The symbol for that is L, and just like the capacitor is characterized by its capacitance C, the inductor is characterized by L. Now, Faraday's law explains how an inductor works. So an inductor is basically like a coil, a solenoid. It's several loops of wire, a wire that has been wrapped around a core, for example. So when you put a current through this solenoid, there's going to be a magnetic field generated by that current. Inside the solenoid, there's going to be a magnetic field. So if we change the current, if for some reason the current flowing through this inductor changes, then Faraday's law tells us that there's going to be an induced voltage across the inductor. The induced voltage has a value of minus d phi dt, where phi is the magnetic flux that is going through this inductor. So an inductor, which is basically a solenoid, would have a magnetic field inside of it proportional to the current. That's what it is for a solenoid. Therefore, the flux will also be, the flux going through the inductor would also be proportional to the current. So we can write this proportionality in terms of an equation. We can say that the flux is equal to a constant, proportionality constant that we call L, multiplied by I. So that L is what we called before the self-inductance. So using L, we can see that the induced EMF generated across the two sides of an inductor is equal to minus L di dt. So when the current changes, the current that is flowing through the inductor changes, there will be an induced voltage across the inductor. The amount of voltage induced through the inductor is minus L di dt, and this is based on the idea that inductors, or what this implies is that inductors oppose the change in current. So for example, assume that we have a current flowing into the inductor this way, as you can see in the picture, and that the current is increasing. The I dt is positive. The fact that the voltage across the inductor is minus L di dt tells us that this voltage is going to be negative. What that means is that the upper side of the inductor in this picture is going to be higher in potential than the lower side of the inductor, because a difference in potential negative, we measure those differences in potential in the direction of the current. So a negative change in potential means the potential is dropping in the direction. As we move through the inductor, in the direction of the current, we must be going downhill in potential. So the upper part of the inductor is higher potential, so we put a plus sign there, and the bottom side is negative. In the case of the current change being positive, increasing current through the inductor. So the inductor, as we can see, develops a difference in potential that tries to fight against, tries to pump current in the circuit that the inductor is connected to. This difference in potential tries to pump current in the opposite direction in which is flowing into the inductor. So that is a consequence of inductors opposing the change in current. Now, if that current that is flowing through the inductor had been decreasing, that means if di dt was negative, then the expression minus L di dt, which turns out to be positive, then would tell us that the difference in potential as we move through the inductor, the difference in potential increases or it rises, which means that the proper signs that we can assign to the potential on both sides of the inductor are negative on the top and positive at the bottom. Now let's put this inductor in a circuit with a resistor. So initially we're going to have a battery that is going to be pumping current through the inductor and the resistor. We have had this circuit connected like this for a while. The switch has been in position 1 for a while. So we have a certain amount of current flowing through the inductor and through the resistor. And what we're going to do is that, well, at this time, when the switch is been closed for a while, there is no potential drop across the inductor, because there is no change in current. The current, as we said, has been flowing for a while, so the current is not changing anymore. So basically the current that is flowing at this moment in the circuit is going to be the EMF of the battery divided by R. The inductor does not have a difference in potential. We assume that they are made with ideal wires, and ideal wires don't have resistance. So that's the situation when the switch is in position 1. So now what happens when we move the switch to position 2? So we move that switch to position 2, which means it takes the battery out of the equation, and what we have now, it's a closed loop composed of only the inductor and the resistor. At the moment when we change the switch to position 2, the current in the inductor that's been flowing had a particular value, and as we know, inductors do not they oppose the change in current. So this inductor is not going to let that current change quickly. It's going to have to change slowly. So that current is going to continue flowing at the beginning in the circuit in the direction indicated by the arrows. And for this closed circuit, Kirchhoff's loop law says that the sum of the potential drops along the path is 0, which means that the potential drop along the as we move through the inductor plus the potential drop as we move through the resistor, they add up to 0. And the first potential drop is minus L di dt. The second one, if we move in the direction of the current, we drop potential as we move through the resistor, so that's minus IR, and those two potential drops add up to 0. So the equation that we end up with here is that di dt, moving L to the other side, equals minus R over L times the current. So again, we have arrived to a differential equation, a simple differential equation of the first order for the current. So if we solve this equation, we'll find what is the current as a function of time for the LR circuit. So this is the equation that we have before. In the di dt equals minus R over Li. We're going to use the same trick that we talked about before. We're going to split the di dt into di and dt. So we're going to send the dt to the right hand side, divide by I on both sides. So we end up with di over I equals minus R over L dt. That allows us to write the integrate on both sides easily. So if we integrate on both sides, we have on the left hand side the integral of di over I, and on the right hand side we have the integral of minus R over L dt. Those integrals are easy. The limits of the integration are, as you can see there, at t equals 0 we had some initial current in the inductor, in the circuit, and after some time t we'll have a different amount of current, and the integral then is, on the left hand side, is the natural logarithm of I over I naught, and the integral on the right hand side is minus R over L times t, and that allows us to find that the current in the LR circuit is also going to fall exponentially. But notice that the time constant is no longer RC. Obviously we don't have a capacitor here, so the new time constant is L over R, the inductance divided by the resistance that we have in the circuit. So a graph of that current is an exponential function, and as before, the current will have dropped to 37% of its original value after a time constant equal to L over R. Now, if we had, instead of setting up the circuit this way, if we had set up the circuit as you can see there in red, if we had the battery connected all in series with the resistor and the inductor, we had a switch, and at t equals 0 we close the switch, then the situation will be different. Now we will have the inductor's current will be initially 0, and as the battery starts to pump current into the circuit, the inductor is not going to let that current to increase very quickly. It's going to have to ramp up, and that current therefore is going to have you can write the equations that apply for that, and you'll find that the current in the circuit is going to go from 0, is going to increase in an exponential way. The function that describes that is going to be of the form 1 minus e to the minus t over L over R, the same time constant, but now the function doesn't decay exponentially, it increases exponentially with an asymptote at the value epsilon, the EMF of the battery, divided by R. So that would be the behavior of the circuit in that case. Alright, I hope that that was clear. I'll see you in the next video.